Hi everyone, this is Bailey.
Hi everyone, this is Bryce.
Today we're going to
graph quadratics.
have fun.
Have fun!
Alright, graphing quadratics is going to be pretty simple. All we're going to do is put a bunch of pieces together that we've discussed over the past couple of days. Let's just go over really quickly some of the characteristics of the parabola, and these characteristics will help us with our graphing. First, a parabola is curved and extends infinitely in one direction. We have the vertex, which is the highest or lowest point on the parabola. We can kind of think of that as our starting point or our stopping point. We also have the axis of symmetry, or the line of symmetry. That's the line that sort of divides our parabola perfectly in half, and we can see that one side mirrors the other side. It also shows that the points on the parabola are equidistant from from the axis of symmetry. We have parabolas that open up, we have parabolas that open down. And if you remember, we have this great pattern that we investigated that we called our over-up pattern. And we used that to help us find additional points on the parabola. And so we'd go over 1, up 1. Over 2, up 4, over 3, up 9, and so forth. We realized that the ups were just the square of the input, and that we would, if we had a value of a, we would multiply that value of a times the ups in order to see if our parabola widens or narrows. The one piece we haven't done yet is calculate and plot the vertex point. Before I get to that, I want to talk to you about the different locations a parabola can be in a coordinate plane. Let's look at when a parabola is in a coordinate plane like this. In this particular example, the parabola has two x-intercepts. It crosses the x-axis 2 times. We call those roots, or we say that this quadratic equation has 2 real answers when y is equal to 0. The reason for that is we're going to look at this one part of the quadratic formula, the plus or minus the square root of b squared minus 4ac, in particular the radicand that's on the inside of that. When that radicand is a positive value, I'm going to get 2 answers. I have plus or minus the square root of a positive value, which gives me 2 things back. That's why I have the 2 x-intercepts. The radicand, b squared minus 4ac, is called the discriminant. And the discriminant gives us, or lets us know, how many real answers we have. And remember, the real answers are just the x-intercepts. So what does it look like when we don't have any real answers? Our parabola might look like this. So it's in the coordinate plane still, but it doesn't cross the x-intercept at all. Well, what happens with that is the discriminant ends up being less than 0 or negative. And remember, when you have the square root of a negative value, that's an imaginary term. And so we don't have any real answers, no real roots to a problem like this. Therefore, there are no x-intercepts. What happens when the discriminant is equal to 0? Well, we can kind of look at this example right here, and I've done the entire quadratic formula, but the discriminant is equal to 0. Well, the square root of 0 is 0, and so I'm just left with the opposite of b over 2a as the x value when y is set equal to 0. Well, this ends up being the vertex because I only have one x-intercept, and that one x-intercept has to be the vertex point. That's the only way a parabola can cross the x-axis, only at one point. A great example of that is our parent function of y equals x squared. We know that the vertex here is 0, 0, and it only has one coordinate point that crosses the x-axis here. what this ends up giving us is the x-coordinate of the vertex for any parabola. And then all we'd have to do is plug this value, this x value, in to calculate for the y. There's a much more formal proof that we can do, and we'll do that in class to show why it's the opposite of b over 2a. But for right now, I just want you to learn how to calculate the vertex. We are going to find first the x-coordinate of the vertex. That is the opposite of b over 2a, which are just the coefficients of the quadratic equation. In order to find the y-coordinate of the vertex, we're going to plug the value for x back into the original equation. So again, the vertex is a coordinate point, and it does have two components. Let's look at our first example, which is just the parent function of the quadratic functions. Here, the value of b is 0, and the value of a is 1. So the opposite of b over 2a is 0 over 2 times 1, or just 0. Plugging that back into the original equation, I get y equals 0 squared, or just 0. And this is exactly what we expected. We know that the parent function has a vertex of the origin, and so 0, 0 is what we get. Let's look at our second example. It's just the parent function with a value of c, negative 3. So that means that this parabola is shifted down 3 along the y-axis. The value of b is still 0, and the value of a is still 1. So that means that the x-coordinate of my vertex is still 0. But by plugging this into the original equation, I get 0 squared minus 3, and the y-coordinate of the vertex is negative 3. And that's exactly what we expected, that we have shifted down 3, so our vertex also shifts down 3. Well, let's look at what happens when we've got some actual values for a, b, and c. The first thing that we're going to do is identify those values. In this example, a equals 1, b equals negative 4, and c equals positive 4. The opposite of b over 2a gives me the x-coordinate of the vertex, and that would be the opposite of negative 4 over 2 times 1, or positive 4 over 2, which is 2. I then take the value for x and plug it back into the original equation to find the coordinate, the value for y when x is 2. That gives me 4 minus 8 plus 4, or negative 4 plus 4, or 0. So this particular vertex is 2, 0. Let's look at our last example. Here, a equals negative 1, b equals 2, and c equals negative 1. The x-coordinate of the vertex is the opposite of b over 2a, which is the opposite of 2 over 2 times negative 1, which is negative 2 over negative 2, or 1. To find the y-coordinate of the vertex, I plug x back into the original equation, and I get the opposite of 1 squared plus 2 times 1 minus 1, or 1 plus 2 minus 1, which is just 2. That gives me a vertex of 1, 2. And I could plot all of these in my coordinate plane, and it gives me a starting point for graphing my parabola. Now we're ready to put all of the pieces together to graph this example. Y equals negative 3x squared plus 12x minus 8. The first thing that I want to do is identify a, b, and c. In this example, a equals negative 3, b equals 12, and c equals negative 8. Then I need to figure out whether this parabola is going to open up or down to check to make sure I'm not making any errors in my graphing. Remember, the value of a tells us whether it opens up or down. If a is negative, it opens down. So in this particular case, that's what's going to happen because a is negative 3. Next, I'm going to calculate and find the vertex. The x-coordinate of the vertex is the opposite of b over 2a. In this case, the opposite of 12 over 2 times negative 3, which is negative 12 over negative 6. So the x-coordinate of the vertex is positive 2. To find the y-coordinate of the vertex, we plug the x back into the original equation. That's negative 3 times 2 squared plus 12 times 2 minus 8. 2 squared is 4. 4 times negative 3 is negative 12 plus 24 minus 8, or 12 minus 8, which is 4. That gives me a coordinate point of 2, 4 for the vertex. And I can go ahead and plot that vertex. 2, 4 is located right here. Next, I want to graph the axis of symmetry. This is the vertical line that's going to go through the vertex and help me figure out additional points on my graph pretty easily based on the symmetry characteristics of parabolas. Here, remember the equation for the axis of symmetry is x equals the x-coordinate of the vertex because it goes straight through the vertex. In this particular case, x equals 2 is the equation for the axis of symmetry. Next, I'll find the y-intercept. Remember, the y-intercept is the point at which x equals 0, or is 0, c, the value of c, which for this example is 0, negative 8. By plotting that, I'm going to start at the origin. I won't move any direction in the x-axis, but I'll go down 1, 2, 3, 4, 5, 6, 7, 8. And here is my y-intercept. The reason why the axis of symmetry is so helpful is because I automatically know, because I have this y-intercept right here, that I also have a point located right here, just opposite the y-intercept across the axis of symmetry. I can also use my over-up pattern to plot additional points. Remember, from the parent function, the over-up pattern is over 1, up 1, or in this particular case, down, over 2, down 4. But because the value of a is 3, I'm actually going to go over 1, down, negative 3. Over 2, down 4 times negative 3, which is negative 12. Over 3, down 9 times negative 3, which is negative 27. That's going to be a little bit off my grid, so I can stop here. But what it does is just help you find some additional points to create your curve. So starting at the vertex, we'll go over 1, down 1, 2, 3, and there's a point that will also be on here. Because of the axis of symmetry, I also know that this 2 will be a point on my parabola. Over 2, down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 puts me right at my y-intercept, which is a point that's already there. The last thing that we're going to do is connect the dots in a nice curve here and make sure we put our arrows at the end of our parabola. And there you have it. Here's an example for you to try on your own. Go through each one of these steps one at a time and see if you can plot the parabola. Pause it, and then in a couple of seconds after you pause, when you come back, you'll see the solution on here. We'll do this more in class, and we'll also talk about graphing from another form called vertex form, which can sometimes be a little bit faster depending on the numbers that are there. See you in class.